Alright everybody, back with another flipped lesson here. Today we're going to be talking about parallel and perpendicular lines. You see at the graphs here on the left we have an example of parallel lines. On the right we have an example of perpendicular lines. I want you to just take a moment to look at them. What do you think you notice about them? Now, one of the major things we should be noticing about these graphs here is that to the right, lines C and D do seem to be crossing at some point here in the fourth quadrant, where the blue and purple lines never seem to intersect. Now those are going to be two characteristics that are going to be crucial in distinguishing and differentiating between parallel and perpendicular lines. So let's scroll down a little bit and look at some basics here. If you're asked to describe what parallel lines are, they will never, ever, ever, ever intersect. So it's two lines that are in the same plane that are never going to intersect. The same plane is a topic you're going to discuss more in geometry. In our class for Algebra 1, we're always going to be talking about lines that are in the same plane. So if the lines are not crossing, they are going to be parallel. On the right, something we should be getting into our notes for perpendicular lines are the fact that they are two lines in the same plane that will intersect at a right angle. And those of you guys unfamiliar with right angles, they measure a 90-degree. And here, the little red box that you see where the two lines are meeting, that's a sign used throughout math to denote that there is a right angle present there. So if you see that in a diagram, it should tip you off that we're talking about perpendicular lines. Now, here, moving down a little bit, we talk about the rate of change here. Now, the reason the parallel lines are going to intersect, they have the same exact rate of change. As this A line is raising, line B is going up at the same rate. So we can characterize their slope as being exactly the same. Now, for perpendicular lines, the slopes are a little bit trickier. We would say that they have a negative reciprocal slope of each other. We're going to talk about what that means. Hopefully the term reciprocal is ringing some bells from when we were solving equations, but this is a slight variation on that. Now, being mathematicians, we do like shorthanded ways to write things, so for parallel and perpendicular lines, that's no different here. So if we're talking about A and B, the lines, we can write it as A is parallel to B using this symbol here with two lines going straight up and down that are never going to intersect each other. Again, just save us a little bit of time when we're writing, when we're describing the relationship between them. For perpendicular lines, if we scroll up, we'll see that I named these lines C and D. So when we're talking about these two perpendicular lines, we can describe it as line C being perpendicular to line D. Now the symbol for perpendicular lines, it's kind of like a upside down T, and if you look at it, it kind of has that 90-degree angle that we should become familiar with seeing in perpendicular lines. Now, quickly moving on, recall that we had this idea of a reciprocal before. It was used to get rid of fractions, whether they be coefficients in front of a variable or in front of a binomial that we wanted to get rid of, and we would flip the fraction around, and that would essentially multiply by the fraction to get us 1, essentially getting rid of it from any consideration. Now, a negative reciprocal here, similar to this idea, but again, the negative adjective there leading off should tell us that something is going to be different. In this case, they're going to multiply together to get -1. So to find this, it's similar to when we would find the reciprocal. We flip it around. If we have some number A over B, we'd flip it to get B over A. But we got to also have this switch coming in after the fact, where after we flip A over B to become B over A, we also got to switch the sign that's in front of it. Now, I don't want you guys getting confused where the slope has to be negative if they're perpendicular. When I say negative B over A here, negative is just changing the sign of it. So if it was negative, it would become positive now. If it was positive, it now is becoming negative. So that's something we should be on the lookout for, and we'll practice this a little bit more in class. Now, why do we need this? Now, chances are most of you guys are sitting in a room right now that has 4 corners. the walls are meeting at perpendicular. The walls are perpendicular to one another. Two of the main places we see parallel and perpendicular lines are in urban planning, layouts of streets in cities and towns, and in architecture. If you were laying out a blueprint for a building, for example, odds are you're going to be using parallel and perpendicular lines somewhere inside there. Now, if we see this is just a kind of generic little map that I pulled off of Google here. You see that these streets, Lewis Street is parallel to Clark Street while also being parallel to John Fremont, while Lemmy Pass Drive and Sacagawea Lane are running perpendicular to them. Now, using parallel and perpendicular lines allows it to be a little bit easier to plan, keeps everything nice and organized, and gives you kind of these nice rectangular blocks to use for houses, parks, whatever. Now, as we're going to be using this a few ways. We're going to be using the formulas we've become familiar with here: slope-intercept, y equals mx plus b, point-slope form, y minus y1 is equal to m times x minus x1. We're going to be using these types of equations. Why? Because we can pick the slope right out of it. Here, the m in both of them is going to be telling us what the slope of that line is. We can use that to find lines that will be parallel to it, perpendicular to it, and that's going to help us write equations for parallel lines. Say we were in charge of laying out streets and we wanted to make sure we were plotting streets that were parallel to one another, or just to double check our work. Say we have two equations already. We want to check to see, are these equations parallel to each other? Are they going to be perpendicular to each other? Or are they just going to be generally intersecting at some angle that's not 90 degrees? So let's take a look quickly. Again, a few types of questions that we'll be seeing on assessments here that I want us to be ready for. One might look something like this: determine which lines, if any, are parallel or perpendicular. Well, in order to compare these, we want to know what their slopes are. So my first thought is, alright, well, line A here, what is m going to be? In this case, m is the 4 that's going to be multiplied by the x. Line B, our m is going to be equal to negative 1/4. And line C, m is going to be equal to negative 4. So now that we have our slopes identified, we want to start comparing. Are there any slopes that are the same? 4 is not equal to either of the other two. Negative 1/4 is not equal to either of the other two. We're not going to have any lines that are parallel to each other, so maybe we should start looking for negative reciprocals. If you saw the negative 1/4 and negative 4 and got excited about that being a negative reciprocal, careful, because those are just reciprocals of one another. The negative reciprocals actually come here and here, so we would actually be able to say that lines A is going to be running perpendicular to line B somewhere on the graph. And if you plotted this into Desmos, you'd see y equals 4x minus 2 intersecting negative 1/4 x somewhere at a 90-degree angle. Now, moving on, let's look at a slightly trickier one before we go on to other types of problems. Now, if we see here line A being 4x minus 3y equals 2, line B equals 3x plus 4y equals negative 1, and line C here being 4y minus 3x equals 20. If you just started picking off, oh, there's a 3 here, or a negative 3 here, a positive 3 here, and a negative 3 here, you'd be mistaken, because we don't have this in a form that is going to allow us to pick these slopes out right away. So we need to take a second and fix that. We need to solve for y in this case to get it into slope-intercept form. So I'm going to take a second, solve for y, show all my work for you guys, so I'll be back in one moment. Alright, now that that's finished here, take a look at what we got. This first equation simplifies to y equals 4/3 x minus 2/3, so we're looking here at a slope equal to 4/3. Again, just going off of our y equals mx plus b. Our second one, y equals negative 3/4 x minus 1/4, is going to give us a slope of negative 3/4. And last but not least, we have y equals, that's a terrible m, y equals 3/4 x. Again, 3/4 being our slope here, plus 5. Now, when we're comparing again, none of these are the same, so we're not going to have any parallel lines. We got to now start looking for negative reciprocals. So any of these flipped and have the opposite sign. So in this case, 4/3 and negative 3/4 would be the ones we're looking at. So for this, again, different setup, but same result. Lines A is going to be parallel to line B. Now, last but not least, you can see the point slope form down here, again, making a return. Like I said before, we're not just going to be comparing to see whether they are parallel or not. We're going to be using these to find equations that are parallel or perpendicular. So we're kind of going to be wrapping this all together, finding the slope using the knowledge of whether a line is parallel or whether a line is perpendicular to kind of dictate what the slope of the new line will be, and then using the point slope form to get a new equation. So for the first one here, we see write the equation of a line that is parallel to y equals 3x plus 4 and passes through the point 5, negative 6. So if I'm looking here, I know that since it's parallel, that's going to be telling me it's the same slope. So in our case, slope will be 3 here. We have our x1, x1 being the 5. Let me just write it a little bit neater. So x1 being our 5, y1 being our negative 6. So we can go straight ahead and start plugging this in. So y minus, and again, since it's a minus a negative 6, I'm going to go switching this to plus 6, is equal to 3 times x minus whatever that x1 is. So here's where it's going to be negative. I know we were getting caught up in class about when are we going to have a negative, when are we going to have a positive. We got to use the formula to kind of tell us when we're going to be using what. Now you could simplify this to be slope-intercept form. I'll do that in a moment, but for now I want to get on to the next one to keep this video as short as possible. So here being a perpendicular line, we're going to be using this slope here 4, but we're going to need a little different slope. So here our perpendicular slope is not going to be 4, but it's going to be 4 flipped, or 1/4, also with a different sign. So where it was positive before, it's going to become negative now. And since we know it's passing through the point negative 1,3, it's just the same process as before once we identify the slope that's going on. So y minus our y coordinate being 3 is equal to negative 1/4 times x minus our negative 1. So in this case, x minus a negative 1 will become x plus 1. And that's really all there is to it. Now again, I know this was a quick recap. What I want us to be focusing on really is up here at the beginning here, knowing how to characterize lines here, knowing we can go by the slope to tell whether something is parallel to one another. We can tell from the slope to know if something is perpendicular with something else. We got to have that with us. We're going to use this a lot going forward. You're going to have it through some of your engineering classes and beyond. So that's really it. Again, if we got questions on this, I'd love to hear them in class, or you can ask them on the YouTube channel even. I'll try to get back to you guys as quick as I can. Otherwise, I look forward to seeing you all in class. Have a good one, everybody.